All right, let's go through a design example. We have a column that needs 450 kips. Axial load, 250 kip feet. Bending, and a shear of 14 kips. We're going to use 4,000 psi and 60 ksi and assume that slenderness can be neglected. So let's see, our first thing we want to do is select material properties and a trial row G. So now the trial row is just to get a guesstimate on our size. Our column size. So let's say, well, our F prime C is 4,000. Our Fy is 60. And let's select a row of 0.015, right? We want between 1 and 3. So you could pick 2. But let's pick 0.015. 1 and 3%, right? Okay, our next step, select a trial size. So if I flip back in my notes, I have a relationship between the material properties and your reinforcement ratio. Let's back a little ways. There we go. Let's assume tied columns. So let's see, our AG trial is greater than or equal to PU over 0.4 F prime C plus Fy rho G. So 450 kips. 0.4 times 4 ksi plus 60 ksi times 0.015. Should get about 230 inches squared. If we use a square column, just take the square root, right? Square root of the answer you get 15.15 by 15.15, right? I just took the square root of 230. So we need to be a little bit bigger than that, so round up. Let's say a 16-inch by 16-inch column. Okay, that's just based off of our material properties and our selected reinforcement ratio. Now that's a trial reinforcement ratio. That's obviously not going to be the one because we haven't designed anything yet. Now let's look at a column type. So select column type using E over H. So let's see, our eccentricity is our moment divided by our axial load. So that would be 120 kip feet over 450 kips. .267 feet or 3.2 inches. Our E over H would be that eccentricity of 3.2 inches and our 16-inch column dimension. So our eccentricity ratio is 0.2. Oh, I meant to write that in red. Oh well. So 0.2. If it was greater than 0.2, go back to the very beginning. We said if it's greater than or equal to 0.2, use a square with reinforcement only on 2 faces. Means we have a fairly high moment. Okay, tied column with bars on only 2 faces. Slenderness. It said neglect it. We could check it, but for now we're just neglecting it. So our trial size is our 16 by 16 column, 2 faces. So let's see, what's our next thing we need to do? Calculate a gamma because we're going to need that to determine which chart to use. So let's say we've got, you can kind of think about how we've done what we've done before, right? D minus 2.5. If you have right from here to here, you have 1.5 inch cover plus, let's say, a number 4, which has a diameter of 1/2 inch. And let's say number 8 right? That's our tie. Number 8, longitudinal. So half a bar diameter is 1/2 inch. 1.5 plus 1/2 inch was 1/2 inch. 2.5 inches. That's typically what we did when we were doing beams, right? Was 2.5 inches, D minus 2.5. Right. To our longitudinal bars here. And if you have 2.5 inches on both sides, then let's see. Gamma H equals H minus 2 times 2.5 inches, because you have 2.5 inches on either side. So gamma is H minus 2 times 2.5 inches over H. Gamma is 16 inches minus 5 inches over 16 inches. So it's almost 0.7. It's 0.6875 for all of you who like your billion. So let's see. Right, all I did was just assume a number 4 tie, number 8 longitudinal bars, and 1.5 inch cover, normal cover, right? So I'm subtracting 2.5 inches from both sides. That's my distance between the centroid of my 2 longitudinal sections. One of them will be tension, one of them will be compression. And that's gamma H, so then I just divided it by H to get what gamma was. So I'm going to go to the interaction diagram. I have F prime C of 4,000, an Fy of 60 KSI, a gamma of 0.6875, and square with reinforcement on 2 faces. So I've got to go to the textbook. That's where these design aids are. So here I have 4 KSI, 60 KSI, and 0.6. And then on the next page, is 4 KSI, 60, and 0.75 gamma. And then I go to 0.9, and then I start to change my F prime C. So I'm gonna have to interpolate my answer. I have 0.6 and I have 0.75. So we're gonna have to use both of these design charts. So I need to know phi PN over BH and phi MN over BH squared. Phi PN over BH, that's my PU over H squared because it's a square. I've got 450 kips divided by 16 inches squared. It wants to be in KSI. So 450 divided by 16 squared, 1.76 KSI. That's my y coordinate. My x coordinate is phi mn over bh squared, which is my moment capacity divided by h cubed. I'm going to want that in KSI too. That's what, 120 kip feet, 16 inches cubed, 12 inches per foot to get rid of that foot in the numerator. So I'm going to go to my two interaction charts and find the what you're going to get out of these interaction charts is the desired reinforcement ratio. So I'm going to need 1.76 and 0.35. So let's see. I wonder if I can make that smaller. Nope. Well, we'll figure it out. So my 0.35 is down on the bottom, so there's 0.3, 0.35. Something like that. Alright, 0.35. And let's see, 1.76 for my y-axis, 1.67. So right here, and that is a little bit before see, this is the 0.01, this is 0.02, so that's probably about 0.014. Now the question is, okay, this is for gamma equals 0.75. So for gamma equal to 0.75, I'm looking at a goal reinforcement ratio of about 0.014. Everybody see how we got that? I went in with my mu on the bottom, mu over bh squared on the bottom, my pu over bh on the vertical axis, found where they met, and then interpolated between rho of 0.01 and 0.02. And just stare at that for a minute just to make sure you see where I got that. Now I'm going to have to do it again on, I'm going to delete that. I'm going to do it again with the gamma equal to 0.6, which is this one right here, gamma equal to 0.6. So take a minute, look at this. Gamma equal to 0.6 using a 0.35 KSI on the bottom and 1.76 KSI. What would you guess for your row? Alright, 0.35. And then let's see, 1.76. So right there. Ay, ay, ay. I don't know. Something like there. So. Yeah. So now we're a little bit past halfway, right? So I'm gonna guess 0.017. Could be 0.016. I mean, you know, this isn't super precise, but just get a general guess. I'm gonna say 0.017. Right, you're between, this is 0.01, this is 0.02. You're a little over halfway between. So, let's see. I'm gonna say 0.016. And now I get to interpolate because I have I'd figured out before that I'm gonna have a gamma of like 0.69. So, oh gosh, I put 0.016. I have to put 0.017. 0.017 plus what? should give you a reinforcement ratio. Now, they're not that much different, right? I don't know. 1525, 153. I don't know. So far, I selected a column type based on, I selected a column size based on a guessed, which is actually very close. Selected a trial size based off of that. So I'm going to say a 16 by 16 column. Because it has quite a bit of eccentricity to that axial load, I'm going to have a square column with bars on only two faces to try to maximize my moment capacity. Calculated my gamma, assuming number 1.5 inch cover, number 4 ties, number 8 longitudinal bars. And then used 2 interaction diagrams to interpolate to find an actual, what we're going to use. Reinforcement ratio, which is very close to the one that I guessed. So let's see, our next is to select reinforcement. So let's see, my area of steel is equal to my reinforcement ratio times my gross cross-sectional area. So 0.0153 times 16 inches squared. You get like 3.9 inches. So that would be, let's see, a number 8 has an area equal to, what, 0.79? So that would mean I'd need .9 number 8s, or if it was number 9s, has an area of steel of 1. And make sure when you're using these areas of steel, use the values in the back of the book. Quite a few people did not do that. I have to go like all the way to the end. Quite a few people did not do that. Do not calculate them based off of the diameters, because that is not the way. This is the way. Alright, what page was that? 581. If you don't have this, if you don't have this tabbed, you should. Right. Use this when figuring out your reinforcement. Alright, a number 8 has an area of 0.79 inches. A number 9 has an area of 1 square inches. Don't use the diameters to calculate the area. Bad students. Anyway, so that would obviously be, if I use the number 9, 3.9 bars. So that's easy enough. I can do 4 number 9s, 1 in each corner. Right? Do 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 do. For number 9s, that'll probably be a number 3 stirrup, tie, whatever it's called. And we've got 16 inches by, that's a tie, not a stirrup, by 16 inches. So there's my designed section. Chose a number 3 because, which we'll have to go back and check it, but a number 3, what page is that on? Column reinforcement. Oh, it's on the next page, is that right? Why? I just wrote this down. It's in chapter 25, right? Ten point seven, 3.1. 10.7. I just hadn't turned the page yet. No, that's the number right there. 25. Column transverse reinforcement. That's what it's called. I was looking for the word shear. Okay, page 499. I have the tab, I just couldn't find it for some reason. Page 499, column transverse reinforcement. Ties. Number 3s for a number 10 or smaller, and we're looking at over 9s. So we'll come back to that, but that's how I selected that. Again, that's on page 499, column transverse reinforcement. Okay, so now let us check the PN and VMN. So what we want to do is calculate the maximum VMN if VPN is PU. So using the design aids, this is already probably fine, but it's always nice to go back. Never mind. What we're gonna do is okay, so if let's calculate what our rho G actually is. Our area of steel over our gross cross-sectional area. So for number 9s, 4 inches squared over 16 inches squared. Our rho G is 4 divided by 16 squared. 0.0156. Our gamma is 16 inches minus 2 times 1.5 inches of cover minus 2 times 3/8 of an inch stirrup minus 2 times 1/2 inch of a number 9. Right, before I assumed number 4s and number 8s, so it's slightly different, so 1.128. Alright, this is all, let's see, right, cover, this is H, 2 times cover, 2 times the diameter of the stirrup, 2 times half dB, right? Number stirrup is number 3, dB is number 9. I'm just going to go back to my design aids and use those to calculate my VMNs. So let's see. Gamma, oh, I'm going to divide that all. Go down. Oh no. Let's see. I'm going to divide that all by 16 inches to get my gamma. That's what, 0.57? Oh, yikes. 16 minus 2 times 1.5. 2 times 3 divided by 8. Minus 2 times 0.5. Is that right? 16 minus 2 times 1.5 minus 2 times 3 divided by 8. Okay, I must have done something weird there. Okay, so 0.695. We can assume it's probably okay, but we'll check. So 0.156, let's see. 0.156 is right in here. And if I needed VPN, what was that, 1.76 KSI? Something like that. That's a little bit like 0.2, right? Basically, since I've already done this already, it's fine. Yeah, just ignore what I've been saying. Since we use the design aids, it should work just fine. Let's do one more thing. We're going to check what's the last one? All right. Let's check shear. So I said number 3 ties. My minimum spacing for buckling that is what was in right. Let's assume this one doesn't apply. So center to center should not exceed 16 times dB of the longitudinal bar. So let's see. It says center to center spacing shall not exceed the least of, so I need to find the smallest. The minimum spacing, or sorry, the maximum spacing is actually what we're talking about here. Maximum spacing for buckling is the minimum of 16 times the dB for the longitudinal bars, 48 times the diameter of the tie bar, right? Or smallest dimension of the member, which is 16 inches. So that is minimum of 16 times 1.128 inches, because I have number 9s. 48 times 3/8 inches, that's my number 3 ties, or 16 inches, because I have a square member. So 18 or 16, so I've got number 3s at 16 inches on center. Is what I need for buckling, right? This satisfies buckling of the longitudinal bars. Now my shear, how much can I get from my concrete? This is just like this is going to be just like beams. If I go to chapter 10 is the column, or is the chapter on columns. There it is. That's walls. So chapter 10 is about columns, right? Where does it start? Chapter 10 is all about columns. So I'm going to scroll down. Required strength, that's fine. Design strength, VN. Axial force, that tells us how do we calculate axial force at the moment. The shear capacity is in accordance with 22.5. So I go to 22.5. That'd be cool if that was a hyperlink, but apparently it's not. 22.5, which is the same that we used for shear, or for beams. One-way shear strength. And this is where we say our shear strength is how much we get from the concrete plus how much we get from the stirrups. So how much do we get from the concrete? VC. Now we actually have an axial load. Let's say what's AV min, right? Let's go back and check. What's AV min? That's back in chapter 10. My minimum shear reinforcement, transverse reinforcement shall be shear. Hold on, where is it? I see it. It's 10.6.2. I was like, I see it. Okay, minimum shear reinforcement. We're in columns. This is chapter 10, which is all about columns. AV min is, this is the same as before. Isn't it? Hose beams. Yeah, it's the same as beams, 0.75 and 50. So AV min is 0.75 square root F prime C, BW over S. So let's see. Because I have a shear force, right, is the maximum of 0.75 square root F prime C BW S over Fy BW times S over Fy T. Assume our transverse reinforcement, let's say it's numbers, it's F, it's 60. So 0.75 square root 4,000 PSI, 16 inches. My spacing, I say, is 16 inches. Over 60 KSI. 60,000 PSI. Or it's 50 BWS over FYT. So 50, that's PSI. 16 inches, 16 inches. Over 60,000 PSI. That's not good. 0.75. So my AV min is 0.21 inches squared. My AV is going to be, right, if I got a crack, like let's say this is my column, these are my longitudinal bars, that's my shear reinforcement. AV is 2 number 3s. It's just like a beam, thinking about it that way, right? But I'm only looking at the stirrups, not the longitudinal bars. So my AV is 2 number 3s. Which is 0.11. So just barely satisfied AV min. Now I can go back to 25, chapter 25, 22.5, sorry. Chapter 22.5 to calculate VC. Page 404. Right, so we're satisfied AV min, just barely. We can use this top one. We do have an axial load, so that is going to help us. So let's see. Since AV is greater than AV min, VC is 2 lambda square root F prime C plus NU over 6 AG BW D. So let's see. Lambda is 1. We have normal weight concrete. NU is our PU. 450 kips. AG is 16 inches squared. BW 16 inches. D is very, very extraordinary. D is 16 inches minus 1.5 inches of cover, minus 3/8 of an inch for my stirrup, minus 1/2 of a number 9. Alright, it should be like 13.56. VC is 2 square root 4,000 PSI plus 450 times 10 to the 3rd pounds. Right, because we want pounds and pounds. 6 times 16 inches squared. Oopsies. 16 inches squared. All that times 16 inches, 13.56. So I get 91 kips, like 91,000 pounds or 91 kips. So if you recall, if we have, so let's go back. We have a VU of 14 kips. Oops. Phi VC is 91 kips times the phi for shear, which is 0.75. .3 kips. If VU is less than half VC, right? I can get all of my, oh wait, that doesn't even matter, right? Because I've satisfied AV min. I don't need any shear strength from steel. Is what that means. No additional shear requirements. If VU was over half VVC, I'd have to have AV min, but I already satisfy AV min anyway. But since I got 68.3 kips from my concrete, I don't need anything with my steel. So my final design is what I had before, right? Where's my thing? I've got a terrible drawing, but right, it's a 16 by 16 inch column. With 4 number 9s as my longitudinal reinforcement and number 3s at 16 inches on center as my transverse reinforcement. That is designing a column. Okay. Thanks.